our program with Brent Doran. And the title of the talk is Applications of Non-Reductive Groups to Quantum Information Theory.
All right, well, thank you very much. So let me first, of course, thank the organizers for the invitation. I'm happy to be here. And second, let me issue 3 apologies in advance. So one is that I was told to make this talk as basic as possible for a mixed audience. And so one aspect of this apology is that I shifted the focus. So rather than the title just said, which I had expected months ago, there'll be some of that, but just hints. You should think of the title as Detecting Genuine Many-Partite Entanglement with the partite particle entanglement by single particle measurements. So that's the theme. We'll say several things about it. And most of what I talk about is going to be joined in various ways with Matthias Christondel, David Gross, Walter, et al. So there's master's students and so on as Matthias who've been working on some of this. And there's a little bit in the background, which I'll try and slip in just a bit about, joint with Francis Kerwin. Okay, so that's apology number 1. Apology number 2 is that I have never lectured on this particular material before. So hopefully it will come across reasonably well at first go. And the third apology is that some of the work I'll discuss about is still in progress. So we can't show you written things for everything. Okay, but now on to the main topic. So we want to address the following basic physical question. So how do you measure entanglement? I guess a fourth apology is for my handwriting. If you can't read something, please just shout out. So the naive expectation you might have is that entanglement is a purely global phenomenon. So local measurements would reveal nothing. So let's say naive expectation. Global. Little to nothing. But let's take a limiting case, which you could actually not just theoretically take as a limiting case, but try and produce something like this in a lab. Take a limiting case. What if the state is pure? So we'll say pure state. And then we can ask, are there interesting constraints? Or you could say interesting and useful constraints. All right, so to begin with, we'll think of this pure state. We're going to have some vector in a Hilbert space, or we'll more commonly be thinking of projectivization, Hilbert space. We sort of need a definition for equivalence of entanglement. Of course, as a mathematician, the first thing you want to do when you define classes of objects is define their maps between them and equivalences, right? So what's the definition we'll use? And it's one that's standard in the physics literature, so many of you surely know it. Equivalence of entanglements. And one nice one, conceptually at least, is that you can take an operational approach in which you say that entanglement's equivalent if operations cannot create entanglement. So operations related to them cannot create entanglement. So let's say operational approach. equivalent if cannot create. Let me flip these. Can I flip these? Yeah, okay. And a little more. There we go. Okay, so what's the point here? So you have what's sometimes called local operations in classical communication, and a small modification of it, but important for our purposes, stochastic. So stochastic local operations in classical communication. Basically, it's this idea, but you allow non-zero success probability. So instead of being guaranteed with your operation to be successful, it's non-zero success. And the advantage, well, there are a couple advantages of this approach, but for us in particular, the advantage is that this gives a very nice, clean mathematical formulation for your notion of equivalence. It really comes down to living in orbits for reductive groups. So, right. So basically, this, yeah, I can pop this wire. So the key point for us is that this notion of equivalence, the idea, that brings in a lot of mathematics. I mean, of course, you could work with LOCC as well, but this is more complicated and that's not nearly as clean. This entanglement class of equivalence is given by orbits of complex reductive groups. So for instance, we could take the case of 3 qubits. All right, so now we could think of SL2 3 times, acting on, if you like, projectivization, the defining representation, turns it up correspondingly. And in this case, if you simply enumerate the orbits for the group action, this is quite manageable. So here you get 6 classes. And in the physics literature, they're commonly denoted GHZ. So we never really do this in mathematics. I don't know of any orbits we typically give names to unless they're somehow, well, yeah. So GHZ, we have W. And then we also have, of course, 3 different biseparable and just the straight product. All right. So in general, of course, if you leave this 3-qubit case, which is very, very special, you'll find some other examples with such finite lists of classes, but in general, you'll very quickly get infinitely many, and infinitely many parameterized by a large dimensional family of continuous parameters. So in general, infinitely many, and we're, of course, classes parameterized by exponentially many parameters. So by sort of e to the number of particles, roughly, continuous parameters. Okay, so quite elementary, but important to keep in mind. And so this is in some sense bothersome, because you really want to think of entanglement as something that you can measure, compare different entanglements. And if you really have all these continuous families, how do you get a hold of them? What's a physical interpretation? A bit difficult. It's certainly not very lab friendly. But the crucial point for us is that this sort of structure brings in a lot of mathematics, and I really mean an enormous amount of mathematics. You could hit it with some of the most sophisticated tools in the mathematician's toolbox, some of the most current techniques from many directions. It all depends what you want to do. So this implies lots of mathematics. The most obvious is, of course, we've already seen representation theory. if you want to understand these continuous parameters of equivalence classes, you can study invariant theory, and we'll need a little bit of that later. So these are all very classical. The problem here is that it's very difficult, as I said, to work with any physical, practical meaning. So, for instance, I can parameterize infinitely many states. But how do you prioritize one over another? In particular, can you measure relative entanglement? So we want to say that one state is more entangled than another, and maybe this isn't so useful for that. But measure. Yep.
Entanglement is very kind of business.
To the end for which?
I thought entanglement is a very metric business.
Yeah, so you could certainly think about this approach as well. Yep. Mm-hmm. But how do you actually? So there's many issues when you start thinking about metrics. I'm not an expert on the physics side, but mathematically, of course, you can think of this as a quotient, and now you have to choose a metric on the quotient associated with an ample line bundle, for instance, and that choice might make a big impact. So you could try and take an asymptotic limit. But
No, but I'm just continue on.
Okay, sure. Okay. Okay. So we want something which ideally is going to be practical in the real world of lab settings. So what's the issue? So first of all, one of the things that makes this so handy for mathematics, so these are very classical things, but there's far more. One of the things, the structure that makes it nice is orbit closures. Sorry. So what do you mean by this? I have my vector v, and I'm simply applying this group action to it, getting a nice orbit, and I can think of this, identify this, with sort of homogeneous space G mod H. So we've seen already G mod P's and so on, but this is much more general. This is just going to be any closed subgroup I can think of, which is then sort of the isotropy group for V, the stabilizer subgroup for V. And let's give a quick example of what begins to happen. I'll give two examples, but let's consider SL2, and let's think of this as my G, and I'll think of my H as just upper triangular. So this is a very simple group, right? It's just an additive group, just translations in the line, but bumped up to a plane in essence, so a shear transformation. And what already happens is kind of interesting. So if you act on your SL2 A, B, C, D on the right, 1, T, 0, 1, and if we did our matrix multiplication correctly, hope we do, then we get A, AT plus B, C, CT plus D, and you observe that these two entries are not changed by the action. So in particular, we can think of these two coordinate entries as being invariant functions for this action. So what does that give us? It gives us a map from SL2 to C2 given by A and C. And we just have a single condition on this. The single condition is that A and C cannot simultaneously be 0. Otherwise, I'm leaving my SL, I'd lose invertibility of the matrix in particular. So the point is that the actual map factors through C2 minus the origin. So I can't have A and C simultaneously be 0. And then this includes here. This seems like a stupid point, but it's extremely important. In particular, it's going to be the source, believe it or not, of an enormous number of the difficulties and interesting techniques that one can use to study the objects we'll be studying, at least in the background. So the point is that here, I didn't hit all of C2. I'm missing something. And so this, we can think of as sort of boundary information that's been lost. But it is there canonically. You could fit it in. So if you wanted to take an orbit closure in a space, you might have the C2 minus the origin. So if I looked at G mod, so SL2 mod, this group, H, I can say that it's C2 minus the origin, but when I take a limit in my ambient space, I'll probably fill in this point. All right, so we need to remember when take closure, this comes back. Okay, that doesn't seem so bad. You say, great, we're back to C2. But the problem is if you work with larger groups and other H's, then this sort of boundary behavior gets almost arbitrarily bad. It's, well, it depends, yeah. There are a lot of subgroups you can pick. And in fact, you even lose canonicality. There might not be any natural thing to fill in, and it also depends on your particular ambient space. Lots of mathematical questions surrounding this, and an example of what can happen with that last comment, as well as introducing these sorts of things that can happen. Singularity is another topic mathematicians love. So let's do a simple, just C star action, t squared, t cubed, and if you want to work projectively, 1, and zeros elsewhere. So what's happening is I can think of this as parameterizing a y squared equals an x cubed, right? So then what that looks like is, here's my axes, my two-dimensional slice, just like that. So I get the singularity, and of course if I change different powers here, then I can get different sorts of singularities occurring. So again, this is itself, the group itself, C star, is quite nice, but C star closure suddenly has the singularities. And so in the geometric complexity talks tomorrow, you'll see important but bad versions of this sort of phenomenon. All right, so this is a very simple explanation case. Other things that pop up very quickly, so orbit closures, the crucial fact here is that orbit closures stratify into orbits. And you very, very quickly get all sorts of famous mathematical issues popping up, like Hilbert's 14th problem. Which, for our purposes, we could say roughly means that so it's a question about finite generation of rings, but here somehow it'll tell us something about G mod H always admitting fairly nasty closures. So this is finite generation of rings. See a lot in the math literature about this. But the way to think of it for us is there's some sort of lack of unique factorization behavior. Some G mod H's always admit geometrically unpleasant sort of V divisor behaviors and so on. Unpleasant behavior. Orbit closures. Okay, so that's just a small taste of very classical issues that begin arising. But for our purposes, let's leave that behind for a moment and just think in terms of what we would like orbit closures to encode from an entanglement perspective. Sort of naively, you would hope, at the very least, that if you give me an orbit closure, then the entanglement on the bulk, the original orbit, is somehow has more information than the entanglement in the closure. So the orbit closures themselves give a natural hierarchy of entanglement classes.
Partial ordering.
Yeah, partial ordering. So as I said, you have your bulk, you have the boundary. I'd like to say that in this interior, this is somehow going to have more information. There's more information here. So I would like whatever hierarchy we might be able to come up with for entanglement to at least respect this hierarchy. So that's one sort of constraint you might want to impose. Okay, so would like a proposed hierarchy. All right, so to address this, it's a question in mathematical theoretical physics. We're going to try and actually pass to some tools that really come from mathematical physics. And mathematical physics is one of these funny subjects where sometimes it's clear what the motivation is, and sometimes people use fancy names to describe things that don't a priori obviously link up with physics. And that'll be a case here. So this is something that was inspired by physics, but is not really physics. But here we're actually going to use it for real physics. So inconveniently enough, at least the direction we'll be talking about, comes from Sir Michael Atiyah, who was actually, the bust of him is right outside there if you want. He was instrumental in getting the funding and political push to get this entire complex built. So it's a very Cambridge topic. But the little quick history there is that the origin was infinite dimensional gauge theory So I'll just say one or two quick words. So ATIA is what I'm talking about basically with bot. There's this famous paper, Yang-Mills equations on a Riemann surface.
This bus that's just outside here.
Say it again?
And it's just
Yeah, it's just there. Look outside the window, you'll see it.
so here.
He's one of the legendary mathematicians of the post-World War II era. And this is one of his, he has many famous papers, but this is certainly one of them. Maybe top 5. What he does is he and Bott study Yang-Mills functional on some infinite dimensional space, it's gauge theory. And so you can think of this as an energy functional. You'd hope there's sort of Hamiltonian notions floating around. And he realized, as often happens in these sorts of subjects, he's working with what seems like a very complex situation, but he realized it generalized down to finite dimensions very nicely. And so this induces, I should point out a couple things. This induces a equivariant and Morse theoretic. Can't explain these terms, even though they're pretty fundamental basic math now. And Morse theoretic stratification of this infinite dimensional space, which can compute many nice cohomological structures. But he realized that there's a finite dimensional version. And the finite dimensional version is of this functional basically gives you this called moment map. That's some Hamiltonian information being encoded in a single map, a list of Hamiltonians in a sense, but equivariantly. So, and furthermore, the stratification information is somehow hidden in a rational convex body called a polytope. So very quickly, let me say the abelian case. So in the finite dimensional case, the abelian case, we have a torus action. So we think of a torus acting on some x sitting inside, if you like, on a full projective space. This is some closed projective subvariety, whatever you'd like to call it. But you could just think of it as the action on projective space if you prefer. You can act via linear representation, right? So my t is acting here, equivariant embedding. And what this gives me somehow is to the data of this action, of this representation, and maybe of this subvariety, it gives me this rational polytope. So it might have, might be high dimensions. The dimension is going to equal the dimension of the torus. And you want to ask questions about how the structure of this polytope encodes information about this action. And it turns out to be quite simple in this case. So you have what's called, the fact that this is a convex body is called the Tia convexity. And you could ask about the non-abelian case. And so to continue the story a little bit, other people have been thinking about non-abelian cases for things as well, but this particular story was mostly Atia's. And he assigned the finite dimensional non-abelian case questions to one of his students at the time, who just started, Francis Crowan. It was a very good thesis project for someone who's very good, as the outcome was extremely good. So the non-abelian case, in the end, the convexity result there, you also appropriately formulated to get a convex polytope, but it's called Crowan convexity. Okay, so this is, sends all background to what was talked about yesterday with Sarah. Apologize. One way to think of this is the vertices of the polytope have a very nice interpretation. So the vertices here have a nice interpretation. There's two, one geometric, one algebraic way of thinking of these. Right, so the geometric interpretation is you can imagine this torus action on my projected thing has fixed points. And you simply want to see where the fixed points go under this map. And some of those fixed points will go to vertices. So all the vertices will be hit as images of fixed points. So images of fixed points. Now mathematicians, especially geometers, love fixed points. Once you have a fixed point, there's usually a lot of stuff you can do about it, in the infinitesimal neighborhood especially, decompose things into sums over local structures about fixed points. The other way you can think about this is weights of the action. And of course, these are basically the same information. Let's think about it a second. If I were to do this diagonally, I can have, a t1 through tn, t to some list of vectors alpha, t1 to tn to some alpha 2, t1 to tn to some alpha k. And all we're saying is that if you know the weights, then you can basically label these points, alpha, just plot them. And it's very easy to see, of course, that this corresponds to fixed points, because if you think of all these coordinates vanishing, then in a projective space, that point is fixed by the T alpha 1 action. So if all coordinates but 1 vanishes, you get a fixed point projectively. Right? Okay, so not much is going on in that sense, but an enormous amount of mathematics begins to come from this. So with the non-abelian case, it's been come up from many directions. So I should say this polytope structure is called in the literature often moment polytopes, or weight polytopes, because of the links with weights, or Kerr-1 polytopes. They're all the same idea. Okay. All right. So let's think about this for a moment. So the abelian case is really nice. What about the non-abelian case? How hard can this be? Well, the first thing you might try, or a thing you might try, wasn't the original approach, but the original approach was more symplectic. One thing you can try in this algebraic setting is quite natural, and that's the following. So you want to think of non-abelian reducing the abelian case. So how can we do this? Well, we can think of our, first of all, set it up like this. G acts on x, and this induces an action on, now it gets a little more complicated, the ring of functions, polynomial functions on x. This is some infinite dimensional vector space because it's a ring of functions. And you can then think of, in G, my maximal unipotent, which is just strictly upper triangular matrices, if you're thinking GLN, for instance, this maximal unipotent, U. And one thing you could do then is you can think of, so this is going to decompose into a direct sum over various highest weights of irreducible representations, right? And you could think then of invariance. So you can simply ask which functions are invariant under this subgroup. It turns out to be a very natural thing to do because it's picking out, if you think about it a moment, it's picking out not the irreducible representation, but a copy of the irreducible representation, and it remembers the weight. So this is equal to now a direct sum of just one-dimensional spaces where we remember the weight. And remembering that weight means that the maximal torus information is still here. Okay, so in a sense, what's happening is this residual T action is giving us, so this residual T action can be thought of as acting on this space of functions which dually has a sort of geometric characterization. You could think of it sort of as some sort of... Yeah, so what's happening is you're keeping the number of irreducible representations as well as the... So this is remembering the number as well as the actual form, right? So you're right that lambda in this sense can have repeats. I'm not saying it's the same. So the residual, I'm sorry? Yeah. So the residual T action then you could think of as some acting on a geometric object, and the problem now becomes very quickly that this object is somehow complicated, partly because of this boundary behavior I was saying here. So you see in this case, 1T01 is a maximal unipotent in SL2, and you get these boundaries. So, okay, well the basic point is that this has a T action. You could imagine that you end up getting a convex hull from the T action just like you do here if you set things up properly. And so you should be able to recover the abelian polytope, and you can check it's the same thing as the non-abelian polytope. So this is, okay, so how to say it. So the polytope is somehow the collection of highest weights rescaled by degree. And I guess the first one who observed this would be Briand. But there are several ways of doing this. This convex hull of remembering weights. Remember weights rescaled by degree of the function. And so I'll mention Briand there. But you could also, from a symplectic point of view, think of this as something called symplectic implosion. Or even Mumford, okay, good, Mumford. So even further back. But Briand sort of exploited this extensively. So for instance, you can recover convexity of the non-abelian polytope from this sort of point of view. But okay, so symplectic implosion. is another point of view on things. Gilman, Jeffrey, Schmar. And that perspective came about quite a bit later, early 2000s. But okay, at any rate, the point is that there are many perspectives on the same objects that give you the same results, and every technique will give you some different strengths, like describing the boundary in some way versus something about functions. But for very small cases, once you have this description, then computing moment polytopes in principle shouldn't be that bad. You'd think that it's simply a matter of computing invariance, and that's true. So you could argue that for small cases, computing can then recover the polytope by computing invariance. And there's a finite generation statement here, so somehow this can be done in finite time. So there's sort of two famous algorithms that are used in principle all the time in pure mathematics and algebra. One is you say, we know that we have finitely generated rings of variance, and they can be computed, at least for reductive groups or maximally unipotent style things. The other is the so-called resolution of singularities. And I would say that both of these theorems are as close to lies as theorems can be, in the sense that the algorithms are horrendous. You never, ever want to actually implement these in practice, except in the absolute simplest cases. And often your intuition is a better guide than the algorithms for what to do in those cases. So in principle, you could always do it. And in small cases in practice, you can recover the polytope. OK, so let's quickly pass to some screen and some examples. Screen? Thanks. OK, so this is the simplest case we mentioned at the beginning. So here we have the 3-qubit case. We mentioned this classification of 6 objects, and you can see for each class, you can look at the orbit closure and look at an associated polytope. And this case is small enough you can compute it in a number of ways. So there's one. That's the product. There's the 3 biseparables. Here is the W state polytope. And here, you get the GHZ state polytope. Okay, so these are well known in the physics community, and in this case it's very nice because the polytopes actually give you bijective correspondence with the classes. So that's useful. And observe, though, there's one very nice feature from a practical point of view, and that's that if you actually applied some sequence of measurements in the lab, and you ended up with your eigenvalues lying deeply in here, far from that wall, then you could conclude that you are not actually in this W state or any of those others, you're actually in the GHZ. So this suggests that there should be some nice way to, in practice, even in a laboratory way, maybe, distinguish classes, give some witness for entanglement. And oops, let me go back to this. So, the point now, the crucial point, is that this polytope encodes an entanglement hierarchy that's compatible with the sort of orbit closure business we were talking about before. And then you can witness entanglement classes in what turns out, after some checking, to be an experimentally robust and efficiently checkable way in real-world quantum systems of any number and statistics. So writing on the side here, the reference for those who are interested. There's a paper from a few months ago that appeared in Science. So with Michael, myself, Abid, Matthias. We tried to write it so it's easy to read. I hope it is. So the polytope, what are the points? It gives, well, one thing that's handy for practical physicists is this gives a finite hierarchy. It requires only linearly many, at least once you set up your purity, requires only linearly many measurements in the number of particles. It's robust against experimental noise, so you can stay close to your pure state. And as I said, you can witness then entanglement classes. in this SLOCC sense. Okay, and finally, it can, at least in principle, be detected by not just abstract techniques in some super lab, but techniques that are accessible by today's technology. Yeah.
What situation?
So the basic setup is you're going to give me some state, D, in my space. I consider the orbit closure associated with a polytope. Now, if,
what's the scope of this theorem? The polytope.
so this is not a theorem. This is a statement about physics.
This is a statement about physics.
Yes. That's why it's a paper in science, not in a math. So there's certainly mathematics involved, but the point is that
I just want to know the polytope of what?
yeah, thank you. So the polytope associated with your orbit closure. I guess that was bad, but thank you.
And what class of orbits and orbit closures are we talking about?
There's no
What
restriction.
group actions on spaces are.
In reality, if you think about it, there's really no restriction. You consider any linear representation of G, take projectization. But for us, in practice, we'll work with systems that are quantum systems. And so you can simply consider, SL2 cross SL3 cross SL4 on the corresponding tensor product space and so on. But there's no restriction on the number of particles or the statistics. In that sense, it's a mathematical statement. It really is about representations. Yeah. But the statement here, robust against experimental noise, of course, if you get really large systems, then you're only going to be robust for certain substructures of your polytope, not for every single reasonable substructure, because it is too refined, unless you have a superlab. But for small systems, it's already doable. Okay. Okay. So that's the, so we'll say it can be detected by current techniques. So when I say current techniques, it really is only a few labs that probably can do it right now, but soon, detected by current labs. Okay, not an easy game, but doable. All right, so that's the sort of physics result. And now let's talk about some of the, let me see, should I go a few more of these? Yeah, so what else do we have? So as I said, there's the basic entanglement criterion for witnessing a state. And then is efficient in that you can do linearly many measurements. Further examples, we have 4-qubit systems. Sure, of course you can do that. You have some bosonic systems. You observe, you get genuine multipartite entanglement in the sense that it doesn't decompose, doesn't have to decompose into a product of others. So yeah. Yep. Say it again? No, you don't need finitely many orbits.
What?
You don't need finitely many orbits. This is
No, but I want to say, in this case,
oh, this case, yeah.
C2 power 4, there is a finite number of orbits.
There's infinitely many orbits in 4 qubits. There's already infinitely many in this case.
No,
No.
but it is Neyman.
But this is the image of any of the polytope for any of for a family. Okay.
Yeah, exactly. So, excuse me. So, I'll go back to it in a bit. You can raise the screen. And I apologize, this is of course taking longer than I expected, which is the downside of not doing a technical talk quite too slow. Raise the screen, please. All right. Okay, so now we are given a quantum system, we actually can begin to play this game then. So we say, all right, how do we actually begin to try and describe these polytopes? Well, I told you abstractly, math tells you there exists an algorithm, but of course this algorithm is almost useless. Even though there's entire books talking about how to do computational invariant theory. All right. So, all right, so recall the difficulties here. Well, the abelian case was very easy. So recall, abelian polytope's easy. Non-abelian, in principle, as I said, reduces to abelian, but this is nasty. There's many ways you can imagine a reduction, but the most direct is the one I mentioned earlier, just sort of, well, yeah, so the point is you have acting on this. So So as I said, computational invariant theory is theoretically always works, but in practice, very bad. So the substitute that you might try to computational invariant theory, everyone in mathematics would do something that hoped that you could use geometric invariant theory. So somehow the point of this is that instead of computing all the invariants, you do some sort of substitutes. There's a criterion called the Hilbert-Mumford numerical criterion, which is more computable. So Hilbert-Mumford numerical, we'll call it in quotes, even though numerical, I won't explain the numerical criterion, which avoids some of this computational complexity. And as I said, ideally, you'd be able to reduce to studying fixed point behavior in a sense. And you could actually, in principle, do this. So ideally, study fixed points or something close to it of T on this and produce vertices. But this is a very hard object to get a hold of. In principle, you can. So the basic statement is, if you like work with Francis Kirwan, identifies vertices in a sort of non-reductive way, but this is not in practice so useful, because the problem is that in addition to being complicated to implement, even Hilbert-Mumford requires a lot of effort, and also you're just producing vertices. Now the problem, if you think about just producing vertices, is we have this big dimensional polytope. You might be clustering in some tiny little bit of the polytope, and physically that's not so useful. So, so you could do inner approximations if you want to terminate early, but it won't be necessarily physically useful until you're completely done. So rather than waiting for termination of either of these, could use either of these techniques to do an inner approximation to the polytope. But again, it's very inefficient. Okay, so there's another thing we can do, which would be related to what Rasser talked about last time. Again, this talk probably should have been a predecessor. And that's, you can look at sort of adapted one-parameter subgroups. This is following this Kirwan development, following Atiyah, and parallel developments by Hesselink, following a tradition set up by Mumford. And of course, a lot has been done since then. So the idea is that you look at this picture. So instead of vertices, we can look at information that gives the dual sort of cutting out hyperplanes. So look at maybe facets. And there's some information that can yield facets coming from just looking at these weights. So if you let the alpha I be the weights for your torus action, you just plot them. Imagine then that you get an abelian polytope, right? Then the point is you can look at the closest point to the origin, right, for some subcollection. So you can run through all subcollections of weights, and you can call that a beta. So alpha is for the weights, beta is for something close. So here's a beta. That'll be the closest point to the origin for this polytope, and in particular, also for certain subcollections of the polytope. You see? So somehow this beta information is giving you this adapted one-parameter subgroup information, really, that Rasser mentioned. So the basic point, I'm too low on time to go into the details, but given your state V, and we're looking at the orbit closure. The orbit closure is actually stratified in a very nice way by somehow this beta information. So we'll call them S betas as you run through the betas. So basically, what this tells me is the following. So formally speaking, yeah.
The betas are, you take for each hyperplane, take the point on the hyperplane closest to the origin? Is that?
Not quite. So let me say you look at any subcollection of weights, and you look at the convex hull generated by that, and you take the closest point to the origin for that. So as you run, so this is an exponential task. As you run through all of your weights, then subcollections of weights. That's a power set operator.
You're looking at, but then.
Huh?
Okay.
No, sorry. Go ahead. No, please. Okay.
You're entitled to look at whatever you want.
Okay. So S beta then is going to be isomorphic to, if you like, the formalism. This might, well, okay. So there's some awful things you can begin writing down that make good mathematical sense, and over characteristic zero field, this ends up being something a little bit nicer. But okay, let's leave it the mathematics. The basic point is that this information, this beta information, ultimately is going to give you the stratification for this space. And that stratification information can be used to ultimately rebuild the polytope. So, all right. So if you know which betas exist, so if know which S betas occur for G dot V bar, then you have a lot of information, right? And you can begin working towards your polytope. So get constraints. And the technical term for what's actually going on here, the betas are living on our polytope, but really you're thinking of one parameter subgroups in your representation acting on your space. So the sort of beta data is going to be the same as adapted one parameter subgroups labeled with an extra distance information, somehow information about the rate of decay. So, and a measure, if you like, a distance from the origin. What's happening is that you're flowing, so one way to think about it, these adapted one parameter subgroups are flowing you for your given V. It's adapted to your choice of V. It's flowing you as quickly as possible to the origin in your Hilbert space. It's the one parameter subgroup that does it the fastest. And that corresponds to the beta, or you can end up thinking in terms of an induced gradient flow on this polytope, which approaches beta. Yes. Okay, so this is work of, if you like, Kemp Hesselink, and this is the Kirwan side. So the task skipping ahead. The basic idea, unfortunately, I didn't get to communicate was the stability and semi-stability. I see 45 minutes have already passed. I hope you don't mind if I'm eating into the question time, because I have to get to the main points. So the task somehow all right. I have to tell you this definition of semi-stability and instability in relation to the map. So let's give a quick slide again. Sorry. Slide. Projector. Thanks. All right, so basic point in invariant theory, we have this geometric invariant theory idea that if you suppose there exists a homogeneous polynomial on your Hilbert space and that the polynomial in your state is non-zero, well then in particular, because it's invariant and homogeneous, you know the polynomial being non-zero means you can't include the origin in the closure of your orbit by continuity of functions. All right, so the point is then that if you want to link with physics, the vector of minimal length on this orbit then satisfies a nice relation. And that relation picks out this locally maximally mixed property. So hopefully that's useful for physicists. But the basic point is that the stable, semi-stable orbits are going to be those that somehow miss the origin when you take the orbit closure. And this can be captured by this property of the moment map, the image of the moment map, your polytope containing the origin. So let's leave that up for a moment and say what's making it practical. So the Hilbert-Mumford criterion tells you Hilbert-Mumford criterion. So instability, so we'll say V in H is unstable if G dot V bar contains the origin. Otherwise, V is semi-stable. So we have the following sequence. It's there's going to exist a homogeneous invariant polynomial, non-zero at P, if and only if your point P is semi-stable, if and only if G dot P bar contains the origin, if and only if the image, the polytope, contains the origin. And the inverse image of the origin is sort of hitting this closest point here. So the inverse image of the origin under the moment map is somehow hitting this closest locally maximally mixed state. Okay, so the basic point of Hilbert-Mumford criterion is that this can be seen by looking at one-parameter subgroups. So it suffices, it's equivalent, to check for all one-parameter subgroups. And the thing you should keep in mind is if you had a diagonal one-parameter subgroup, it's easy to see what's happening, TA1, TAN. So in particular, let's just draw one on the plane. Let's say T inverse. You see here, if I pick the point 1, 1, then I have a sort of hyperbolic path given by this orbit, just like in that picture. But unstable things that flow into the origin will correspond to where some of these coordinates vanish. So if this coordinate vanishes, then we flow into the origin. If this coordinate vanishes, we flow into the origin. So here, like that. So those are somehow, these axes are problematic, but the hyperbolic orbits, they're unstable. The hyperbolic orbits are semi-stable. Okay, and then the one problem is if you actually want to use this criterion in practice, is it involves an enormous amount of computation, but it's far, far better than anything else. So I have to skip to the crux, I guess. Sorry. So observe that SL2 acting on C2, every point is unstable. Right? So why is that? If you picked a point, then there always exists some element of V that whose closure contains the origin. But if you try and use one-parameter subgroups, you have to find the right one-parameter subgroup. So non-diagonalizable, or non-diagonal, I should say, tori are crucial. Okay, so keep in mind, again, if I use this TT inverse, then I got the hyperbolic path. But if I take a conjugate of this, as I change my basis, then, so I have these as the axes, for instance, then relative to the corresponding conjugate tori will flow into the origin. So the basic theorem of Kempf, supplemented by Hesselink, tells us there always exists such a nice one-parameter subgroup, although possibly in a non-diagonal form. And in fact, it's unique once you choose a maximal torus. So with that in mind, so Kempf says that there always exists unique adapted one-parameter subgroup given maximal torus. And if you try and adapt what's going on in that world to an algorithm, then it takes several steps, but an algorithm for computing instability, and in particular for computing betas. We'll call it computing instability slash the beta information for V, then things look really good in a sense. You have to do a power series expansion in T's, you adjust for weights and so on. But when you write it down, you end up having, unfortunately, at one stage, to solve a system of polynomial equations in many variables. And so this is the crux of the matter in a sense. This is in a way why ultimately computing polytopes from any point of view is quite difficult. In order to do this, you need to use one of these things that endless books and articles are written about, but in practice are problematic, derivative bases. So to actually find a solution to a system of polynomial equations is actually surprisingly hard algorithmically when things get large. The basic point is that though if you try and do this technique appropriately, instability beta testing appropriately adapted, you have shifting tricks you can use. There's several steps you can apply that are deterministic in principle, compute, but in practice will be hard, and you can boost them numerically. So, so there's just two things I'll end with, a picture and a statement, and then a sort of statement about the future. So, okay. So we saw with Racera's talk that it's extremely difficult to compute polytopes even when there's lots of symmetry. Our problem, unfortunately, is completely general. Once you want to do it for any orbit closure, that's the same as solving it in complete generality. So computation, deterministically, is unfeasible except in very special classes, even though in principle you can do it by a couple of different ways. But what you can do is you could try and do numerical approaches, which maybe are good enough in some cases. And there's two main aspects and one minor aspect. One thing you can try and do is adapt the method of gradient flows following Kirwan. And that's here. Oops. Uh-oh. Play. Okay. So you see if you do that, then you can have some fun. Gradient flow, you actually can sort of numerically do, although of course they're cumulative approximate errors that have to build up. But you can see gradient flow is slightly non-trivial. So here's a case where you start in the GHZ state and your beta is 0. So you try and gradient flow to your beta, and it does work. And here in W, you start there, same place. You try and gradient flow to the closest point to the origin on this hyperplane, and you do, but it has to go through a slightly wiggly route. So gradient flows, but accumulate error. The other thing you could do is you could sort of shifting tricks with coadjoint orbits, and there you can have the advantage that if you're picking something randomly to get something generic choices are a funny thing in algebraic geometry, but with coadjoint orbits it's reasonable with Haar measure, and instability is such a high codimension issue in a sense, and finite issue that it's a very reasonable thing to do. Trick. And use Haar measure to select random numbers and check instability at points randomly. And the final issue, as I said, which you really can't get by, even if you're just evaluating instability at points and doing these beta things at points, in addition to the exponential number of betas, is unfortunately at some stage you're always going to be stuck with this Grosvenor basis. All right, so that's so this somehow is a nicer mathematical approach, which is much more likely to sort of work in general if you could overcome the Grosvenor basis problem. And so I guess I'll end my discussion of this before one last hope by saying that that this is something, these Grosvenor basis issues, the world expert in them, Bernd Sturmfels, or a world expert, I recently heard a talk of his in Vienna, where it's quite nice. He sort of built his career partly on these things, but he was indicating that they almost never work in practice. And he's become a huge fan of numerical algebraic geometry, which involve these sort of random choices, which are very hard to do in practice in algebraic geometry. But he's convinced that in practice for applications especially, this is the way of the future. So hopefully when I chat with him some, we'll see if there's any hope to improve that. Final comment. This is a subject where I focused on something which actually is extremely classical by now. There's a subset of mathematicians who know it well and use it, but there's an enormous range of other mathematical structures which come into play directly tied already to this, or more abstractly. So there's Okunkov bodies. So I've advertised to anyone out there, Okunkov got a Fields Medal. His early work was sort of approaching moment maps and moment polytopes and related structures from a nice perspective. It was inspired by thermodynamics, but has in the mathematical physics vein, actually has very little to do with thermodynamics. It would be lovely to have a quantum interpretation, a real physics interpretation. And also, there's a host of techniques. The instant you're working with this stuff, and there's lots of techniques which you could think of coming from algebraic topology or motivic structures, motivic cohomology. Who knows, maybe quantum cohomology actually does enter into these quantum systems, as Risser touched upon in his lecture, and so on. And in my work with Kirwan, somehow some surprising things enter when you adapt these moment map techniques to non-reductive structures. You can say a lot about geometry. So yeah, I'll end there in the hopes that maybe some people can, over the course of the conference, tell me if there's any hope of interpreting something like the Kuhn-Code body physically. Okay, thank you.
Exciting talk. Any questions?
So I kind of missed the connection between entanglement and the orbit structure. Like so how are you going to measure entanglement?
So the measure of entanglement is so you're using SLOCC notion of equivalence, and then what we're doing on top of that, because that's very very fine, you're coarsening it with this polytope classification. So the measure of entanglement is the polytope class of entanglement, if you wish.
Right. So which ones are very entangled? Which ones are not so entangled? That's what I'm.
Yeah. So if you think about this picture here, well, the completely separable state, the product, is way up there in the vertex, farthest from the origin, right? Whereas the GHZ state, which people like as being very entangled, is the full polytope. So what you have is that direction.
But this is no. I'm talking about when you have n vector spaces and
Yeah, so it's the same game. So larger polytope is corresponding to something which is more generic and
it's
is
the
more
dimension of the polytope then.
No, it's more. It's a partial order structure on the polytopes for your orbits. So if you look at G dot V bar, you're going to have a decomposition to a union of orbit closures, a union of orbits and hence of smaller orbit closures.
And then you want to coarsen that to these polytopes.
Yeah. Okay.
So how does this compare with, say, tensor border rank?
I can't answer that directly. I guess Matthias would have a better chance.
That's sort of a standard
question. Do you think you do?
measure that.
Sure.
That's a single integer.
Would you like
I
to?
don't know. I mean, the states of fixed tensor rank also give you polytopes. If you take the states of fixed tensor rank, that also will give you polytope. And but I don't think we know yet how this ties in.
So
one of the things one.
So I know several different completely natural stratifications of the space that you. Let's just stick to n copies of CD or C2 even.
Sure.
There's numerous, or at least several that I know of, natural stratifications that come from geometry or the group action. And since I'm not a physicist, but I'd like to help to the extent I can. I'd like to understand better which of these stratifications are going to be useful for this business. And
Sure. I mean, in this case, the
So I don't-
stratification is nice because it's directly how you measure the eigenvalues nicely. The stratification reflects this moment polytope structure, which is understandable, comprehensible in a nice way. But I agree, you could certainly look at some different stratification of the space. Look at the image of the.
I just want to know what the relative advantages and what's this one buying you that makes you so happy with it.
Yeah.
And then I could say, well,
So-
maybe I know something better than this, or maybe I don't. But until I know what criteria you're using, it's hard for me to.
So I guess the apart from sort of computability aspects and the mathematician's answer, the reason these stratifications are so nice is they're equivariantly perfect, at least for smooth things. So they're equivariantly perfect.
I
So
don't know what that means.
so somehow the point is that these S betas, you could think of your variety as decomposing into these strata, and look at the cohomology of the variety, the equivariant cohomology of the variety, and it decomposes into an equivariant cohomology direct sum of the open stratum and these other strata. So this is sort of the gradient flow aspect of this stratification. It breaks up your space into cohomologically nice pieces.
But this is you've also picked a torus, right? For this professor.
So so there wasn't a choice of torus that you have to make to set up the problem and get these images. But I mean, you have to pick a T-dual. So this moment polytope lives, the image of the moment map is actually in K-dual, where K is the maximal compact. And then you are picking a torus to slice, but the moment polytope is independent of the choice of T-dual and K-dual. So.
Question or comment. So I got the impression that the main task that you want to perform is to compute these moment polytopes in interesting situations. And there is a lot of mathematical theory, but if you want to apply it in these complicated examples, it's infeasible.
So the question comes down to this: if you have
or not, or this,
so there's multiple levels. So one question certainly is computing moment polytopes, and we have some world's experts in the audience right now, and they've already told you, in fact, that even in nice, highly symmetric cases, it's very difficult, and you try, and even in those cases, use your computer even when you have the answer, and your computer crashes fairly quickly, right? So even when you have this description of hyperplanes cutting out the cone or cutting out the polytope, if you like, things crash fast. So it's not so much. The better way of thinking of this is from a practical physical perspective. If you're in the lab, all you need to do is not compute the polytope, but simply produce enough separating hyperplanes so that you actually get something useful. And what I didn't get a chance to say, because I got through only 2/3 of my lecture, I apologize. An outer approximation, not the inner approximation. And so that follows immediately from a single application of this algorithm. You already get a separating wall at least if the orbit is unstable. And so you don't care about what's happening elsewhere for certain crude questions. And to be honest, in practice, most questions in the experimental world are pretty cruel. Crude. They're cruel too, but they're crude. So yes. But what you're talking about, geometric complexity, of course, you have a very particular problem. And this is, of course. Yes.
I wanted to use this idea, but then I realized there is no, this cannot work because the polytope is everything.
Oh, yeah, that's typical. So if you do a generic orbit closure, then of course so take your representation, do a generic orbit closure. The polytope is the polytope for the full projective space. And that was described already, even more generally for flag varieties, but that was described already in Racera's talk, how to do that in principle. But yeah, you don't want generic. Typically, you want very special.
No.
In your case, was sufficiently generic that you actually got that.
I don't think so. If you take a determinant, but I will talk about it tomorrow.
Okay, then also you could do blow-ups, partial disingularizations. There's a host of techniques you could try, but yeah.
Maybe one more question.
Do you define a particular stratification of the moment cone in case you have continuous families of orbits?
Yeah, so if you have continuous families of orbits, this is a good point. So what you really want to do is to do an instability test for some subvariety or some subspace. And so you could set up the problem in a way that it looks like you're writing down, you have some continuous family of polynomial equations that are simultaneously being solved, but this is just bad. So what you want to do is use the fact that semi-stability is an open condition, instability is a closed condition, and then admit the very small possibility of error, and just do something numerically. So as I said, use the Haar measure approach to sample, to do a shifting Drake Haar measure, then you're not going to be wrong. Instability somehow it's a very algebraic condition, but yeah.
There are not any more questions. Let's thank Brent once more.
Thank you.